Hello engineers, welcome back. In this video, we're going to start a new topic which is called dynamic programming. I hope you're ready. Let's get started. So in this video, we'll see what is dynamic programming, how to identify a dynamic programming situation, which is characteristics of dynamic programming, and we will see the two techniques of using dynamic programming, and we'll discuss the time and space complexity of each method. Okay, let's get started. So what is dynamic programming? So just like our previous techniques, right? Like greedy method, recursion method, hashing method, prefix sum, bitwise operators and things like that. This is also another technique. This is also another, you can say, technique or approach to solving a software question or handling a data structure, right? So what is what are the characteristics of dynamic programming? When should we use dynamic programming? So to understand this, let's take an example of the Fibonacci number. So what is the Fibonacci number? Let's quickly recap. So this is the Fibonacci sequence. So the first two elements are 0 and 1, and every element that comes after that has a relationship with the previous two numbers. So the next number is the sum of the previous two numbers. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and so on. So this is the Fibonacci sequence, right? So how did we solve this problem? We have solved it earlier using recursion, right? So what did we say? We said if this is my function fib n, we said we identified the base case. If n is less than equal to 1, then we simply return 1. And if not, we do fib of n minus 1 plus fib of n minus 2, and we return this. So this was our recurrence relation. Sorry, this was our recursive case, right? So let's build the recursion tree for this. So let's say my n is 5. So in this case, 5 is not less than or equal to 1. So we go into the recursive mode. In recursive mode, this 5 is making two calls. 5 is calling on 4. And when 4 is called, again we are checking. Is 4 less than or equal to 1? No. So 4 is again making a sub-recursive call. This is fib of n minus 1 again. So 4 is making a call on 3. 3 will make a call on 2. 2 will make a call on 1. And this is where we check. If n is equal to 1, return 1. So this is where we start returning, right? And when we are here, 2 will make a call on n minus 2. So 2 will call on 0. 0 is also less than equal to 1. So 0 will start returning from. And from here, the returning will start, right? This is returning. And 3 will call on 1, right? And 1 will not call on further recursion because 1 is the base case. And then this will return. So 4 will call on 2 again. And 2 will call on 1. And 2 will call on 0. And that's it. And it is returned to 5. So now what will 5 do? 5 will call on 3. 3 will call on 2. 3 will also call on 1. 2 will call on 1. And 2 will also call on 0. So this is the entire recursion tree of Fibonacci number. So let's see if there are any problems associated with this recursion concept, right? So the first problem is there are repetitive calls being made. For example, 0 is called here, here, and here. 1 is getting called here, 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 and here. So there are repetitive calls made. This concept is called overlapping subproblem. The same subproblem is being solved multiple times. That is why it is called overlapping subproblem. And there is another relation we can see. The value of 3, let's say the value of 3 is dependent on 2 and 1, right? Is dependent on the subproblem 2 and the subproblem 1. The value of 4 is dependent on the subproblem 3 and subproblem 2. So there is a substructure involved. This type of pattern is called optimal substructure because the current problem is dependent on the previous subproblem, or you can say the current problem can be solved using the previous subproblem. If we see this type of structure, we can use dynamic programming to solve it. Okay, so these are the characteristics of dynamic programming. Wherever you see overlapping subproblems, you can use dynamic programming. Wherever you see that there is an optimal substructure, that you can solve the current situation using the previously solved situation, that's when we can use dynamic programming. So how does dynamic programming look like? Let's discuss the two techniques involved in dynamic programming. First is memoization, second is tabulation. Let's see memoization. Memoization says, in both these cases, what we'll do, we will create a new DP array, which is dynamic programming array. So we make a new space. So we are taking additional space. We will take additional space to solve these problems and improve our time complexity or improve our program efficiency, right? So let's see how memoization looks like. So in memoization, what do? We create another array, we call it DP array, of the size of n plus 1. Let's say my n is 5 in this example. So I will take a DP array of size n plus 1. So this will have indexes up to n. 0, 1, 2, 3, 4, 5. So there are 6 elements in this. That's why it is n plus 1. And I will initialize everything with -1. Now I can use this DP array to make conditional checks to avoid the first problem, which is overlapping subproblems. So what do? Whenever I'm going to solve a problem, I can come and check here whether it has already been solved. So for example, if I go all the way down to 0, and this is where my returning starts, right? So at this point, I know the answer to 0. 0 will return 1. So at the index 0, I will replace it with the answer of that function. Whatever is the solution given by the recursive call, I will store it here. Similarly, when 1 is called, I will store the answer 1. When 2 is called, I will store the answer 1 plus 1 is 2. Sorry, when it was 0, the answer is 0, right? 0 plus 1 will now become 1. When 3 gets called, I will store the answer 2. When 4 gets called, I will store the answer 3. When 5 gets called, I will store the answer 5. That way I will fill my DP array. Okay. This is in this execution. In this execution, we have used this execution. We have filled the array. Next time when something is called, like the right subtree, next time when 1 is called, we know that 1 is already solved here, and we can use the DP array to check. Next time when 1 is called, instead of solving it again, I can check in the DP array. I go to 1 and ask it, do you still have -1 or do you have something else? If it is -1, it means that it is unsolved. If it is anything other than -1, it means that it is solved. So when it is already solved, I can directly take the answer from here and return it. I will simply say if dp of I or dp of n is not equal to -1, then I will not make the recursion call. I will simply make dp of n. I will simply return dp of n. So I can stitch this piece before making the recursion calls. That's it. If I do this, if this condition is satisfied, then I will return from here. If not, I will make the recursive calls. That's how we solve the overlapping sub problem using memoization. Now let's discuss the tabulation method. In tabulation method, what do? We again take a DP array of the same size of n plus 1. So 0, 1, 2, 3, 4, 5. This time we will start filling it from here and we go all the way up to n. So how do we fill it? In our Fibonacci case, we know the answer to the first two steps, right? First two values. So we can directly put those values here, 0 and 1. And to get the next value, we do the sum of previous two elements, right? So 0 plus 1 becomes 1, 1 plus 1 becomes 2, 2 plus 1 becomes 3, 3 plus 2 becomes 5. So I will fill this array. When I have filled this array, all I need to do is return dp of n. dp of n, if n is 5, dp of 5 is here, and I will simply return this, and this is my answer. So how do we fill the array? We know that first two elements are already known. dp of 0 is 0, dp of 1 is 1. And we'll start filling it from the next element onwards. Int I equals to, I will go all the way up to n I plus plus. And I will say dp of I equals dp of I minus 1, which is the previous element, plus dp of I minus 2. And I will return dp of n, because my answer is in dp of n. So this is another method. So we have used the dp array here. We started filling it from 0 up to the given n value, and then we filled it using some logic, and we are returning dp of n. So that is the second method. This is called tabulation method. So we will discuss two methods. This is called dynamic programming. Okay. Now let's discuss time and space complexity. As we already know, this recursion is of time complexity 2 to the power n. 2 to the power n, because every n is making two recursive calls and it is an exponential operation. Now let's see how did we do with memoization. In memoization, we did an additional check. We introduced a check in between. That way, whenever we are solving a repeated subproblem, we don't solve it again. We don't do all this. We don't do all this. We have already solved it. We don't do all this. So we are only doing linear operations. For example, if n is 5, how many operations did I do? 1, 2, 3, 4, 5, and 6. There are only 6 operations. Or you can say this is similar to saying n operations. Close enough to n. So I can directly say that my 2 power n got reduced to O of n. This is O of 2 to the power n, which is very bad. This is acceptable. But in order to do this, I have used some additional space. So in our 2 power n case, we have not used any additional space. So this was O of 1. Using memoization, we are using additional space. This will become O of n. And this is memoization. For tabulation, let's see how we did. In tabulation as well, we have used additional space, which is the DP array, and we have used one loop, which will go all the way from 2 to n. We can say this is O of n operation, because depending on the size of n, this loop will have almost n operations, right? So we can say this is O of n, and space as well as O of n. These are much better when compared to 2 to the power n. Okay. Now this concept is called dynamic programming. Now let's code it and see how it looks like. So we'll solve the same Fibonacci problem using memoization and tabulation. Okay, let's start. So I'm here. We have the same 509 Fibonacci number question. Let's solve it using memoization. So for memoization, we said we'll create a DP array of size n plus 1 and initialize it with all minus ones. So let's do that. We'll create a new vector of int. We'll call it dp vector, and this will be of size n plus 1, and all values are initialized with minus 1. Okay, and we will pass this to a new function. Let's call this function as, let's say, memoization, and we will pass in n, and we will also take our dp vector and we will take it by address. Okay, now we will pass this dp vector to our memoization function along with n, and whatever this is returning will be our answer. Now we have n here and dp vector here. So what do? We already know that dp is initialized with minus 1. So now we can do our same recursion logic. We will build our base case, which is if n is less than equal to 1, then we will simply return n, and we will use our recursive case just like before. We are saying memoization of n minus 1 and memoization of n minus 2. This time we will also need to pass the dp vector. So whatever this was returning, we used to directly return it in our previous recursive case, right? But in our memoization case, we will do an additional check. So let's call it dp check. If dp of n is not equal to minus 1, which means that it is already solved, then you simply return dp of n. No need to solve it again. But if it is not solved, you save it. dp of n will have the answer. dp of n will now carry the answer to this problem, and we will simply return dp of n here. Okay, that's it. So this check will reduce our overlapping subproblems. Okay, let's run it and see. That's it. We can submit. So now this has better performance. Previously it was 2 to the power n. Now this has reduced to O of n. Okay, so this was the memoization technique. Now let's solve it using the tabulation method. In tabulation method, we don't need to initialize it with anything. We said we will create a dp vector of size n plus 1, and we'll start filling it from 0. So how do we fill it? We already know the answer to the first two elements. dp of 0 is 0. dp of 1 is, we will start filling the remaining values using a for loop. Int I equals to I less than equals n I plus plus. So how do we fill it? In our case, whatever is the current I, dp of that I will have a relation with the previous two elements, right? So if dp of I will have the relation with the previous two elements, which is I minus 1 and I minus 2. And if we add them, we get the new value, right? So that's how we filled it. And we will simply return dp of n. That's it. Let's submit. Oops, we have made some error. So here we forgot our base case. Base case is if n is less than equal to 1, we don't need to do anything. We'll simply return n. Otherwise, we will build the DP array. That's it. Okay, so this is the concept of tabulation method. So here we have used the DP array, which is one-dimensional. There will be other problems where we will build the DP array using two-dimensional arrays, but the concept remains the same. So we have used additional space to improve our time and space complexity. Okay, so this is the introduction to dynamic programming and the characteristics of dynamic. So I hope you found this video helpful. Thank you so much for watching, guys. We'll pause here. And if you have any questions, definitely ask me in the comment section. And don't forget to leave a like if you found this helpful. Do subscribe to the channel and don't forget to bookmark the playlist so that you don't miss out on a future video. Thank you so much for watching, guys. I'll see you in the next one. Yes.